The latest project I'm involved with, which I find tremendously exciting, is linking a biological brain to a physical robot, like a metallic robot. So it's giving a robot a biological brain. Now, I'm holding here what looks like a dish. It is in fact a multi-electrode array of a different type than the one I had implanted. This one's quite a flat array. What that means is that around the outside of this array we have little black dots. We can connect onto those with different voltages, with different signals, which ultimately we take from the robot. And in this dish we grow a biological brain. At the present time we take the brain cells from a rat. The cells are separated using enzymes and then laid out in this little dish where we grow them. We feed it every couple of days using a pink liquid that, very much like the athletes use at the Olympic Games, it's got minerals, nutrients that anybody would drink to make them healthy. Well, they make the neurons healthy. Every couple of days we feed it, give it some more food, and it grows. Within 1 week the neurons have linked together, starting to form a brain, and we then take some of the innate activity of the brain. We can apply signals to some of these electrodes, see how the brain responds in a reasonably reliable, repetitive way. So we take some of the innate behavior and use that to drive the physical robot around. The robot has ultrasonic sensors, like sonar sensors, so when it comes near to the wall, we get signals which we use to stimulate the brain and take output from the brain to change the direction of the robot. And hence, what it's trying to do is to move around in the corral without bumping into the wall. At first, the first week or so that we use it, it starts to perform okay, but it's not particularly that good. It bumps into the wall on quite a few occasions. But over the weeks, the brain typically is controlling the robot for 1 hour a day, and after a while, purely the habit of controlling the robot in the way we want makes the neural connection stronger. We can actually see under the microscope how the neurons link more strongly with each other, the pathways strengthen, and so the robot becomes better and better at moving around in its corral without bumping into the wall. It's the sort of thing, if you or I do something habitually, we get better at doing it, and sometimes we might say, oh, it's automatic. Well, in a sense, it does become automatic. The pathways in our brains actually strengthen, so we can be doing something without thinking about it, if you like. The pathways are so clear, we do it in a sort of automatic way. That tends to be what happens with the rat brain robot that we've got. We're actually doing the research for a number of reasons. One is purely from a basic scientific point of view, to find out what happens in the brain. Can we teach the brain in different ways? Can we give it rewards? Some of this we don't have answers to at the present time. But we also want to see, when we put the robot in different positions, how do the memories of those positions materialize in the brain? Some scientists, Susan Greenfield for example, say, well, memories are more diffuse throughout the brain. They're not in one position, they take the whole of the brain. Others, maybe myself more, feel memories are perhaps more partitioned into particular points of the brain. The critical element is, how do we get hold of those memories? Now, this clearly links to problems for humans, such as Alzheimer's disease. If we can learn and understand memory, what it means in a brain, then perhaps we can treat it more closely with stem cells, for example, or even injecting new neurons into the brain, if we know how to do that, if we know where to do that. So there's lots of potential spin-off for this research as far as helping people from a medical point of view. At the present time, we're using rat neurons to drive our robot around. Typical numbers would be something like 100,000, maybe a maximum of 150,000. So it's a reasonably powerful brain. Perhaps not if you're a human, but if you're a slug or a snail, you'd be very happy with 100,000 neurons. In the future, though, we're looking to use other neurons. One example would be neuroblastomas. Now, these are cancer cells which are much tougher than biological neurons. We can grow them into neurons, but maybe ethically it raises a few questions. If we've got a robot being driven around by neurons that were originally cancer cells, people are going to be happy with that. Now, the same is true because we're looking to do this research to help with medical advances for human brains, such as Alzheimer's disease and stroke. Clearly, it's much better to use human neurons. And certainly that can be done, and that's something we are looking to do in the very near future. But of course, ethical questions are raised. If we grow human neurons, 100,000, maybe 200,000 of them, to drive the robot around, it could be seen as a robot with a human brain of a type. For research purposes, that's great, but ethically, well, it might be that not everybody is happy with that. We've got to see. One of the most exciting areas of artificial intelligence at the present time is genetic algorithms or evolutionary computing. This is using some of the ideas of evolution as originated by Charles Darwin and so on, using some of those ideas to improve artificial intelligence systems. Now, essentially, they operate by having a number of possibilities. For example, if I have the robot here and we have several artificial brains, one of them might be better at operating the robot than others. So we need to measure which one's best in some way, either mathematically or get the robot to move around and see how it performs better. And then the better brains, if you like, can be mixed together in a genetic way, taking some of the important features, how many neurons they are, how they're structured, what the basis of them is, and to mix those around and produce the next generation of brains for the robot. In that way, a genetic or evolutionary programming approach can be used to improve the behavior, in this case, of the robot. Examples of using this technology, one is with the National Grid network, when alarms go off if there's a power failure or a lightning strike. Clearly it's in the interests of the company to reconnect the power as soon as possible. It can take a human expert several minutes to work out the best rerouting procedure. Using a genetic algorithm, all of this can be tested within a split second and the rerouting can be carried out. Another example was more of a fun element. We used a genetic algorithm because of its creativity, because it can try all sorts of different solutions, in many ways, in ways that the human brain can't. It can look outside the box. And we used it for mixing pop music. We actually had the four younger brothers of Elvis Costello, they're called Manus, which is Elvis Costello's real name is Declan McManus. Manus was the name of his four younger brothers' pop group. They played some music for us, and we had a genetic algorithm which we called Gershwin that mixed the music for us and came up with all sorts of different solutions based on the original recordings that had been made by the pop group. So we can use genetic algorithms to come up, even within an artistic area, to come up with new solutions, new creations. And I think for the future, genetic algorithms, evolutionary computing, is certainly going to be used much more in an application area, but very much in an artistic way as well. When the steam engine was invented, it revolutionized the world completely in all sorts of ways. In the field of cybernetics now, we see things like that happening, and in the next few years, even more things are going to change completely the way we live. We can see at the present time cybernetics helping people with disabilities, helping people who are paralyzed, move around, control devices, virtual reality systems. So for complete new designs, these can be imagined and interactive with completely in a simulation before they're built for real. But if we look to the future, it gets even more strange but exciting. One of the things that I was able to do with my latest implant was to link directly with my wife. She had electrodes implanted in her nervous system as well. We linked our nervous systems together. Every time she moved, my brain received a pulse. It was a new way of communicating, just as the telegraph and the telephone changed the way we communicated years ago. So in the future, we'll be able to communicate directly from brain to brain. Thoughts, imaginations, pictures, graphics, colours, a whole new way of communicating that will completely change the way we live. Of course, when you link your brain with a piece of technology, you don't need to press buttons to switch on switches. Just by thinking about it, the technology will respond. So in the future, we won't need to press buttons like that. The machine will operate itself.